Okay. Uh, Good afternoon, everyone. I'm Kaushik Sen, and this is CS70, which is discrete math and probability theory. So we have two instructors in this course, Satish Rao, who has been teaching this course for a long time, and myself, I'm Kaushik Sen. And this is one of my favorite subjects, and I kind of did it a couple of times. I haven't taught it directly, but this is kind of the concepts and the ideas and the things that we learn in this course are I apply them day to day in our research in programming languages and AI and everything. So this is a fundamental course that you need to know the concepts here if you want to do anything in future about computer science, discover algorithms, or write programs. So we have right now, we can do programming and we have microprocessors. So we have superpower, okay? So when we write a program, what happens? Or some kind of powerful programs, what it is supposed to do? We have to reason about that program or processor in a logical way, and we have to introduce various kind of proofs. And whenever we think about any kind of concept, human beings, we always think in terms of recursion and induction. We do count quite well compared to other kind of other than humans. So, so before I go into that, Satish, do you want to actually introduce and do something or say something about the course?
No, that's fine. I agree with all that. I guess I'll be teaching the probability section, but yeah, really happy to be co-teaching with Kaushik. So Professor Sen.
Oh, nice. Thank you. So I'll be teaching the first part of the course, which is the discrete math part. And then based on those understandings, Satish and Professor Rao will be teaching the probability theory. And probability theory is something very important nowadays because our world, the way we see it, there are lots of noise, there are lots of uncertainties. And if we want to reason about those uncertainties, all those noise, in the presence of noise and uncertainties, we have to make predictions, and those predictions may not be always true. So one of the question is, if we just say that something is going to happen, and if we do not quantify it in terms of probability, then we do not have an understanding or a quantitative understanding of what is going on or what we are predicting. So probability is important because in uncertainty, you can always give an answer or do a prediction, and at the same time, you can associate a probability with it to give a confidence that how likely that particular event is possible or not. So probability is important, and Professor Rao will cover it in the second part of the course. You also look at the chat and question answers. So this is my first time teaching online. Good. So my hopes out of this course, so at the end of the course, will hopefully be able to teach you how to think more clearly, formally, and precisely, and more powerfully. And also how to deal with and reason about uncertainty itself with probabilities. Yeah, so the probability unit is how can we talk about the how to predict the unknown future events, for example, gambling profit or rainfall or traffic congestion or the stock prices. Okay, so it models the overall system, including the sources of various kind of uncertainties. And for modeling uncertainties, you need some quantitative notion of uncertainty, and for that we develop probabilistic models and techniques for analyzing them. And there are also deductive models which extract the trend from the previous outcomes, like linear regression from the previous history and previous outcomes. And then based on that, it creates a model or fits a model. And then based on that, it can actually predict for a different event in future. So these are called the deductive models. So some administrative stuff. The course webpage is available at this website, ecs70.org. All the policies about grading, office hours, homework, midterm dates, finals, etc. are posted there. So that is the website you should really consult when you have any questions. There will be one midterm and one final. And to have some kind of equity, we have set up the midterm and the final. Like if you perform poorly in the midterm and if you do really well in the final, we'll transfer some of your points from the, or add to the points of the midterm based on the points in your final, and vice versa. So this gives you the flexibility. If you had a bad day during the midterm, you might use the final to make it up. Questions, if you have any questions, please post it on Piazza. The staff or the instructors will respond to it in time. Here you can post questions about logistics, etc., content support, other students, and plus Piazza hours. And there will be weekly post. It's weekly. You'll get a weekly post. Please read it. We'll do various kind of announcements, logistics, and critical advice in that weekly post. Okay, so having said so, let me get into the main content of today's lecture, and I'll start with a puzzle. Okay, so suppose we have 4 cards on a table. The first one is about Alice, second is about Bob, third is about Charlie, and fourth is about Donna. And I pick the name in a way so that their initials are A, B, C, and D. Okay. And each card, one side would contain the destination, and the other side of the card will contain the mode of travel. And there is a card associated with each person. Okay. Now, consider the theory that we want to check or prove. If a person travels to Chicago, they flies. Now, we want to prove this theory, and we have certain facts. Suppose these are the facts I can see. These are the cards I can see for Alice, Bob, Charlie, and Donna. So it says that Alice went to Baltimore, but on the other side, we do not see. It tells me whether she drove or she flew. Same thing with Bob. Here we see the other side of the card of the Bob, where we know that Bob actually drove, but we do not know which city he went to. Charlie, we know that he went to Chicago, but we do not know whether the mode of transportation. For Donna, we know that she flew, but we do not know where she flew to. Okay. Now the question is, which card should we flip to test the theory? Okay. So it requires some thinking. You have to logically think about the different cards, and you have to answer this question. So let's put a poll.
Poll should be launched.
Okay, and C, a lot of C, B, and then almost no A and D. Okay, very good. So what's the answer? Okay, I'm not going to give you the answer right now. Sorry. You thought about it. Let's try to answer this question in a formal and logical way. Okay, so wait for the answer. Thanks for participating in the poll. I think the majority said C, and then a large fraction of the remaining said Bob. Okay, so let's see. How can we reason about this logically? Okay, good. So here is the outline of the lecture for today. Note 0 is background, and you have to read the note 1, which you are already posted. Do read it. So we are talking about the language of proofs, how you can express different kinds of concepts in this world mathematically or logically, and how you can prove them uh, in a formal way, in a mathematical way. So we'll introduce propositions, propositional forms, implications, truth tables, quantifiers, more about De Morgan's law, and after that, I will be able to answer, with those machinery, I'll be able to answer the question that I asked in the puzzle before. Okay. Uh, okay, so let's try to see some examples of proposition. So what is a proposition? Proposition is a statement which could be either true or it could be false. Okay, so let's try to understand. We have a bunch of statements on this slide. The first statement is square root of 2. The question is it irrational? So is this a proposition? This statement, square root of 2 is irrational. Is it a proposition or not? It's a proposition because the outcome of this value, irrespective of what we have put, the number 2 or something else, it will actually come up with an answer true or false. So its outcome is true or false, so it's a proposition. Okay. Then how about this next statement, which says that 2 plus 2 is equal to 4? Is it a proposition? Well, if you check whether 2 plus 2, whether it is equal to 4 or not, it can have an outcome, which is a Boolean outcome. And in this case, in this special case, it is going to be true. So it's a proposition. Okay. How about 2 plus 2 is equal to 3? I know this statement is correct, but is it a proposition? Yes, it's a proposition because its outcome could be either true or false. And in this case, it is false. Okay. So there's another statement. The fourth statement is 826 digit of pi is 4. So is it a proposition? Well, you might wonder whether it is true or false. Despite that fact, it has an answer. It has a concrete answer. So it evaluates to either true or false. And I don't know what the answer is. Let's see. The answer in this case is going to be false. No, the 826 digit of pi is not 4. But still, this statement is a proposition because it could be either true or false. Let's look at this fifth statement. So all these statements or propositions that I stated are true in some context. In the context where we have the notion of natural numbers and irrational numbers and integers and so on, in that domain, and we have the axioms for the addition, for square root, we know how to perform those things. In that domain, all these 4 things that I showed are propositions because they can have only a true value or a false value. Now, let's look at the fifth statement. Johnny Depp is a good actor. Would you call it a proposition? Well, not sure, because good actor, it has different meaning under different context. It has to be kind of calibrated with respect to the user, to the person who is making this statement. Okay, so there is no concrete notion of a good actor unless we have quantified the notion of a good factor using some features and attributes of Johnny Depp. Okay, so in this case, I would not say Johnny Depp is a good actor. It's not a proposition. Okay, now let's look at the fourth one. Any even number greater than 2 is sum of 2 primes. Okay, what do you think? Is this going to be based on your knowledge of arithmetic and number theory? Can you say that this statement is going to be true or false? And it's going to be an unique answer, not dependent on any context or subjective things? Yes, I think it's a proposition. Its outcome will be true and false. But I don't know whether it's true or not. It is actually false. How about 4 plus 5? What is the outcome of this statement? It involves something like x. No, sorry, 4 plus 5. So what is the outcome of this particular statement? It could be a number. In this case, the number is 9, right? So the outcome is not true or false. So we'll not call it a proposition. How about x plus x? Okay, we do not know the value of x. It's not given to us. And also x plus x, if we assume that x has type integer, then it's not going to return true or false or a Boolean value. So it is not a proposition. Okay. Now, given our example that I showed you and the cards that you can see, whether the statement that I mentioned, Alice traveled to Chicago, is it a proposition? Yes, because the answer could be true and false, and you can precisely answer it, okay, based on the cards that you have seen. So it's a proposition, and it's false because she went to somewhere else, right? Baltimore, I think. Yeah, so that gives you an idea what we mean by proposition in logic. Now, there is another statement, I love you. Whether it's a statement or a proposition, is it a proposition? Well, I don't know. I mean, it's again very difficult to quantify and assert and say that whether it is true or false. So, yeah. So this kind of, again, we define proposition as kind of a statement whose value is going to be either true or false, okay, in a given context. Okay. Now, we have this kind of propositions. We saw that their values can be true and false. Sometimes their values could also depend on the value of the variables that you're using in that proposition, and we'll get back to that. Now, we can actually combine these propositions and create more complex propositions, which are called propositional forms. And this is something you have already done, knowingly or unknowingly, since you have started talking. You have developed a logical reasoning capability over time, and you know how to reason logically. And we'll utilize that to derive all the proofs and other things that we're going to do next. So, so propositions can be put together. And here is one way you can put propositions, P and Q. So if you have two propositions that say it's raining outside, and let's say that proposition is P, and Q is another proposition which is say I'm getting wet. Okay, so then P and Q means it's raining outside and I'm getting wet. So both those facts are true. Then this statement, which is a propositional form, is also true. So in summary, P and Q is true if both P and the proposition Q are true. Else it is false. If one of them is false, then this entire propositional form is false. So disjunction is another thing. You can create a propositional form by combining two propositions using the disjunction operator or the OR operator. And it means that P or Q is true if at least one of P or Q is true. Else, this proposition P or Q, it's a propositional form and it's going to be false. So note, in every case where you are forming a new propositional form, it's a proposition because it can have an outcome either true or false based on the values of the propositions it is composed of. Negation is another operator that you can use to construct a propositional form. And here it means not of P. It means that not of P is true. This particular proposition or statement is true if the inner proposition P is false. Okay. So this way, by using this kind of operators, logical operators, and, or, and not, you can actually form very complex propositional formulas. Examples. Is this a propositional form? Not of 2 plus 2 is equal to 4. Yes, it's a propositional form because we have a proposition which is 2 plus 2 is equal to 4. Okay, and that is a proposition, and we know its value is true. And then we are applying this operator negation to this proposition to get another propositional form or a compound proposition whose value is going to be false. Another example, you can take two propositions which could be false or true. 2 plus 2 is equal to 3, 2 plus 2 is equal to 4, and the disjunction of these two, if you combine them using the AND operator, you get another proposition, and that proposition is going to be false. Similarly, we can also combine these two propositions to form a propositional form by joining them with the OR operator. So here I'm saying that 2 plus 2 is equal to 3, or 2 plus 2 is equal to 4. At least one of them is true, which is 2 plus 2 is equal to 4. So this entire propositional form is also going to be true. Good. So this is what we mean by propositional forms. So put together, if we put them together, suppose we have, let me give you an example. Suppose there is a proposition P1, and it says that person 1 rides the bus. So this is true. The person 1 rides the bus. And P2 is another proposition, which is person 2 rides the bus. And but we cannot. Then we have this statement, but we cannot have either of the following happen. That either person 1 or person 2 ride the bus, and person 3 or 4 ride the bus, or that person 2 or person 3 ride the bus, and that either person 4 rides the bus or person 5 doesn't, right? Now, my question is, so we have a proposition for each person 1, person 2, person 3, person 4, P1, P2, P3, and P4. The question here is, can you express this statement in this logical form using this propositions P1, Pi's, and the operators that introduce logical operators and, or, and negation? So what would be the answer? Well, you can see the first thing is you have person 1. So we cannot have either of the following. So what we can have, let's express that. So that is the expression within this and this parenthesis. So that says that either person 1 or person 2 ride the bus. And that is given here, P1 or P2, right? Then this is conjuncted with another propositional form, which is either person 3 or person 4 ride the bus. So this is expressed here, P3 and P4. And since there is an and between these propositions, we connect this propositional form and this one with the and. So this takes care of the first part of this statement. Then we have another or and another propositional form. I know you have all sorts of parentheses. It gives you a cancer of parentheses since it's like Lisp programming. So, but it makes the machine easy to read, and it can read it very precisely, the parentheses. So the second statement is person 2 or person 3 ride the bus, and that is expressed as P2 or P3. And then we have another proposition, which is either person 4 rides the bus or person 5 doesn't ride the bus. And here we have a small change, P4. I'm asserting whether P4 is true or not of P5 is true. That is, person 5 doesn't ride the bus. So this kind of this propositional formula written in using the logical connectors and mathematically is a formal description of the statement that I made above here. Okay, and if you kind of parse them both, you'll see that the parentheses and everything are added properly so that you can connect the propositions which are supposed to be connected together and so on. Now, based on this propositional form, this is true. Okay, and then I took the negation, but we cannot have either of the following happen. So I took the negation, and this is kind of a statement, propositional form that is given. and we understand that this is true. Now, based on this fact, can person 3 ride the bus? We want to answer this question. We want to answer the question, can person 3 and person 4 ride the bus together? How are we going to answer this? So one way, one idea is you can say, let's look at the first question, can person 3 ride the bus? Well, there is one way to express it. You plug in the value of P3 to be true, okay, in this logical form. And then you try to see if the entire logical form becomes true or not. Okay, so we'll get back to that. But this kind of questions we can ask, and it kind of gets complicated. Can you tell me whether can person 3 and person 4 ride the bus together? So we need a way to keep track of things, right? You have to plug in the different possible values of P1, P2, P3, and P4, and then you have to consider the various cases, and then we can answer these kind of questions. And one of the things that usually we try to do is consider all possible values of these propositions, P1, P2, P3, P4, and P5 in the previous case, and create a huge table where we assign all possible values to these propositions P1, P2, P3, and up to P5. And then we plug those values in the propositional formula and check whether the entire formula becomes true or not. Okay. So this is what we call a technique to check if a propositional formula is true or not. And let's go over a simpler example. So let's take the example where we have two propositions, P, and the other proposition is Q. Now we say that P and Q is true if and only if both P and Q are true. So now we can create a table where we have columns for the propositions P and Q, and we have a column for the outcome, which is the value of P and Q. So let's see, if P is true and Q is true, what's going to be the value of P and Q? Based on the definition, P and Q is true if and only both P and Q are true. We can say that P and Q is true because both P and Q are true. What happens to the next case? You have true and false. So P and Q, what it's going to be? One of them is false. So both of them are not true. So it's going to be false. Same with the case where P is false and Q is true. And with the case where both of them are false because none of them is true. So both of them cannot be true. So it's going to be false. So this kind of table defines a function. Depending on the values of these atomic propositions that you see in a propositional form, can you determine the value of the entire propositional form? And this table actually helps you to map out that function. Similarly, we can also have a propositional form which is P or Q, and it is true if one of P or Q is true. And you can consider all possible values or assignments to P and Q. For example, P could be true and Q could be true. In that case, I know either one of P or Q, P or Q is true. So we can safely say that P or Q is true, right? Let's consider another case, which is P is true and Q is true, false. In that case, we can also say P or Q is true because at least one of them is true, which is P is true, right? Good. So this way we can create the table, and you can see that only if both P and Q are false, we get false. Now, one thing, one notion that is satisfied by this kind of propositional forms are commutativity. So if you have a propositional form which is P or Q, P and Q, then it is equivalent to Q and P. Equivalent means whatever value you pick for P and Q, and if you evaluate the value of P and Q, that will be same as the value of Q and P. Okay, so the order doesn't matter. Same thing is true for the disjunction. For example, I made this statement, it's raining outside and I'm wet. I can also restate the same statement without changing its meaning, where I can say that I'm wet and it is raining outside. It doesn't change the meaning of the sentence. So they are equivalent. Um, one use for truth tables is to prove the equivalence of propositional forms. If you have two propositional formulas and you want to check whether they are true or not, or they are equivalent or not, that is for all possible assignments to the values of P and Q, we get the same value for the two propositional forms that we need to check, and we can use a table for doing that. Now, suppose suppose we are given two logical forms, two propositional forms, not a P and Q, and the other form is not P or not Q. So we can actually say or assert that these two propositional forms are equivalent. How can we do that? Well, we create a truth table for each of these propositional forms. Okay, truth table. So I create a truth table where I have all possible values for P and Q in the first two columns. And then I have two columns for the values of the two propositional forms, which I am trying to prove they're equivalent. Now, if you if you say that P is true and Q is equal to true, then you can plug in those values in the formula or the propositional form in the third column. And if you plug true or true, that is going to be true, and negation of that is going to be false. So this is going to be false. However, this one, not of P, it's going to be false, and not of Q, which is again going to be false. So false and false is going to be false, right? So this is how we can fill up the entire table. And you can see that the two columns, the last two columns corresponding to the two propositional forms matches in the values of those forms match for any specific value of P and Q. You pick any value for P and Q, the values of these two propositional forms match. So in that, and because of that, we can say that these two propositional forms are same. So I just showed you a very brute force way and a simple way to prove that two propositional formulas are equivalent or not. Whether two statements are making the same same proposition or not, we can check by using a truth table. You know what? In this example, we proved some famous theorem, some basic theorem in propositional logic, and that theorem is called De Morgan's law. So it says that if you take the negation of a conjunct means a propositional form where two propositions are connected by conjunction or by and if you take the negation of that, that is, if you say it is not the case, both P and Q holds, then we can say this is equivalent to not P or not Q. This is what we just proved. So this entire thing is a true fact. And you can see that the statement that I said, it is not the fact that both P and Q are true. It can be written as in the following way. It is the case that either P is not true or Q is not true. So if you think carefully, these two statements are kind of equivalent. They're equivalent. And if you want to do it very formally, instead of doing it in the brain and cases, you do it using the truth table. And that's exactly what we do in our brain. So this is one way to do proofs. You can also do the disjunction. It's the symmetric version. So you can say if it is not the case that both P or Q are true, then this is equivalent to B. You just push the negation and flip the operator, or becomes and. So it becomes, it is not the case P and it is not the case Q. Okay, so this is kind of the symmetric opposite of the 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 equivalence that I proved using the table. And this kind of equivalence you should remember, because the thing that I'm going to show you next, where I can do certain proofs without creating the entire truth table, there it is kind of very useful. Okay. Okay, so quick question. What do you think about this propositional form, which is T and Q? Is it equivalent to Q? Yes, because as you can see that you have restricted the value of P in this table. So P can now only assume the value true, but Q can assume the value of true or false. So if you look at the first two rows of this table, you can see that P and Q is same as the value of Q, right? So if you look at this value Q, this is same as true, and this one is also same as this value false. So based on this truth table, I can say that true and Q is equivalent to Q. Okay. Let's look at the other thing, which is P, F and Q. Okay. So in this case, all you have to do, is this going to be equivalent to something? It's going to be equivalent to false. You are right. We were posted. And what is the reason? Because if you look at the value of P, where it is the rows where value of P is false, these two rows, you can see that P and Q is false. So no matter what the value of Q is, it's always going to be false. So this is going to be false. The other thing we can ask the question, what is T or Q? And by same reasoning, we can say that true or Q. If you look at this table where we have the true for P and Q, so here you see that the value of P or Q is same as true. No matter what the value of Q is, it is going to be true, right? So this is true. How about false or Q? This is the interesting case. So I know that P is false. So we have to look at these two rows, and then we have to basically decide based on Q whether this propositional form is true or false. So this we can say, if Q is true, then this propositional form is true. If it is false, then it is the propositional form is false. So we can essentially say that F or Q is equivalent to Q. Okay. So these are some of the facts we can prove. And the reason I'm stating this kind of observations is I'll show you next how you can prove various kind of very complicated propositional formulas that they are true without using the truth table. And that is how often it is done in practice, because it's very expensive to check. If you have lots of propositions, it's very difficult, exponential in the number of propositions to check whether the proof holds or not. Okay? So it's expensive. Just going back to the slide on De Morgan's law, here it essentially says that if you have a negation at the beginning of a conjunction, then you can push the negation and flip the sign from conjunction to disjunction, right? It is kind of distributing this negation across the propositions. And you can distribute if you change the logical connector, which is and is changed to or. Okay, so this is what we already proved, but I'm trying to explain it in a new way, in a new perspective. You kind of distributed this negation and pulled it down towards the propositions. Okay, so let's see. Now we want to prove that P and Q or R is equivalent to P and Q or P and R. And this is an interesting kind of a logical or propositional form because it kind of shows how to distribute and over or, as if suppose you are trying to distribute multiplication over sum. So treat the and as multiplication and the or as sum. And if you are trying to distribute it, what you do is P star Q or P star R. So similar thing we did here in logical form. It says that either P or Q or P or R. Now you have to prove this fact. I mean, you can always hand wave and say it looks like a true, but you have to prove it formally. Now let's simplify the case. We already know the fact that if true and any proposition Q is equivalent to the proposition Q. The other fact that we know is false and any proposition is going to be false. So these kind of things we already showed in the previous slide. Now let's try to use this fact to prove this equivalence. So let's consider the case if P is true, okay? So if P is true, what happens, we get this left-hand side becomes T and something else. Something else is some logical form, okay? So this very much looks like this form, where essentially I have replaced this Q with Q or R, right? So it doesn't matter what Q is. If there is a true at the beginning and you are taking the conjunction with Q, you always get the value of Q, okay? So if you replace this Q with Q or R, this is going to be equivalent to Q or R, right? Sorry, Q or R, yeah, this is going to be equivalent to Q or R, okay? And right-hand side, can you also simplify that? Well, if you plug in the value of P, what happens is that you get true and Q or P and R, right? Now you have to simplify it. And again, you can use these relations to simplify it, right? The things that you have already proved in the previous slide. And what would be the simplification? True and Q is going to be Q. True and R is going to simplify to R. So what we get? Q or R, right? So in the case where P is true, we get two symbolic expressions which are syntactically similar, Q or R, okay? So this, in the case P is true, the left-hand side is equivalent to the right-hand side. For this, to prove the fact that the left-hand side is equal to the right-hand side when P is true, I didn't use any truth table, right? I just simplified using the existing propositions that we proved. I used that to prove the equivalence. So this is another way to prove two propositional formula or forms are equivalent without explicitly creating the entire truth table. Okay. You have to also consider the other case where P is false. In that case, what happens to the left-hand side? Well, you have false and something. And you know false and something is always going to be false because both things needs to be true in conjunction. So the left-hand side is going to be false. What about the right-hand side? It's false and Q. That is going to be false. False and R. It is also going to be false. So false and false. False or false, what is it going to be? It's going to be false. So this is also going to be false. Okay. So we consider both cases of P, the case where P is equal to true and P is equal to false. And in both cases, we didn't end up using the truth table. And still, we proved the fact that the left-hand side is equal to the right-hand side by splitting into two cases and by using a fact that we have proven before using truth table. So in summary, what we have done is using this thing T or V equal to Q and all these formulas, you basically simplify it and you prove this fact that if you distribute this P over the conjunction Q and R, you get P or Q and P or R. And for that, you have to use these facts. True or Q is equivalent to true, and false or Q is going to be Q, the facts that we proved in the previous slide. Now distribution is interesting. I introduced this law of distribution. It seems to hold even for logical reasoning. How about a form of this form, A or B and C or D? Can you quickly distribute it? Actually, it reminds me of the FOIL concept that was introduced, I guess, in when my son was in seventh grade, no, fifth grade or something, in the context of arithmetic. And there, what we said is A plus B times C plus D. We applied this concept of FOIL. It means first you have to combine the first two, which is A and C, and you have to take the conjunction of them. And then O means outer, you take A and D, you take the conjunction of those two, A and D. Then I stands for inner, so B and C, those are the inner two propositions. And then L stands for last, so the last propositions are B and D. So you take B and D, and if you take the disjunction of all these conjuncts, you get an equivalent form, where you have distributed A or B over C or D. Okay. So another example of FOIL where you just switch, replace OR with and with OR. Similar, you can also prove it using the way I did it, and the same kind of distribution happened. Yeah. Now comes implication, the most interesting thing in logical reasoning. So I'd like to take a break of 2 or 3 minutes, and I'll restart at 1:30. O stands for outer. Thank you. Uh, Good question. What would be A or B and A and B? What if A is true? A is true, then the first propositional form A or B is true, and it depends on the value of B. Yeah, you can apply the FOIL. Oh, no, you cannot, right? No, you can still distribute A and B, or B and A and B, and then you can simplify them. FOIL is just tells you how to distribute over disjunction or conjunction. Okay. So if you take this thing A or B and C or D, FOIL 1, and you want to distribute this, combine this A, C, B, and D using the conjunction, the AND operator, and then connect them using the OR operator, the way, so you are basically distributing it. And for that, you can use a simple rule that we learned in our uh, elementary or middle school, and that rule is FOIL. So basically, it tells you on the right-hand side, how do you combine the predicates. So if you look at the first propositional form, A and C, okay, so it's the first. You are taking the first proposition, sorry, you're taking the first proposition from this propositional form and the first from this one, from this propositional form. And you are taking the conjunction of them. Then O stands for outer. So what is the outer one? This is the outer proposition and this is the outer. So you combine A and D. And similarly, B and C is the inner. B and C, these are the inner things, and B and D are the last. And you combine B and D. So that's what while means. Okay, let's get back to lecture. Implication, yes, everything has an implication, unless the thing that you're doing is false. Okay, I'll explain that. If the work that you are doing is nothing, then there is no implication. Otherwise, if you do anything, there is an implication. What does P arrow Q means? It means if P is true, then Q is also true. And this is, we use a lot of time in English, right? Whenever we are making a statement in our natural language, we use if then, right? It's quite natural. Here we have, let's assume we have two true statements. One is P, it's a logical, it's a propositional form. And the other propositional form that we have is P implies Q. So these are the two statements that we have, okay? Now, the question is, if these two things are true, we can we conclude that Q is true? Yes. The statement, you can see that if you stand in the rain, then you'll get wet. So this is a statement which has the implication form, if P, then Q. And then let's assume the P is also true. That is, you stand in the rain. Then Q is the proposition which says you will get wet, right? So in that case, statement is stand in the rain. This is one of the statement that you know it's a true fact. Then can you assert that you'll get wet is also a true statement? So that is the question we are asking. Another question is, if a right angle triangle has side lengths A, B, and C, such that A is less than or equal to B, which is less than or equal to C, what happens if C is greater than both A and B in a right angle triangle? Anyone? C becomes the hypotenuse, right? C becomes the hypotenuse, and then we know by Pythagoras theorem, A square plus B square is equal to C square, okay? So if in a triangle, if these properties are satisfied, A is less than or equal to B or less than or equal to C, then we know the statement on the right-hand side is also true. So these are examples of in English language, what we mean by implication. So here the proposition is P, which is a right triangle has side lengths A less than greater than B and less than greater than C. And Q has this thing, which is again a propositional form, which is proposition A square plus B square equal to C square. And we are given the fact that P holds. And based on that, we can definitely conclude from the first two statements, we can conclude that Q also is true. So this is kind of a natural way we speak and how we interpret in natural language the implication. Okay? Now, one funny thing about the implication, sometimes people tend to misuse the implication, and I'll show you. And that's where we get into a lot of trouble and we deduct facts that are not true. So the statement we have is P implies Q. So non-consequences and consequences of implication is So this statement is only is false if P is true and Q is false, right? That is the proposition P holds, and it is not the fact that the Q holds, right? So you say in the triangle the side lengths are A less than B equal to less than or equal to C, that holds, but and it's a right triangle, but the right hand side doesn't hold, and we know that this statement cannot be true, right? So this entire statement Q must be false. So false implies nothing. If your antecedent or the statement that you are making is vacuously false, then you can say anything about the Q. It could be true. Sorry. If it is false, then it implies nothing. So P false means Q can be true. Okay. Or it can be false. Okay. So P is false, it doesn't matter. The prior is not true. That is, we do not have a right angle triangle where these conditions hold. So in that case, it doesn't matter. A square plus B square, it could be true or false. It doesn't matter. The entire statement is still going to be true. And false implies nothing, and anything implies true. So P can be true or false, okay, if what? If Q is going to be true, okay. So if Q is true, if you know, then P can be either true or false, okay. And I'll go over an example. So if the chemical plant, so this is a statement, this is an implication statement. If the chemical plant pollutes river, fishes die. Okay. Now we have two propositions here. One is this chemical plant pollutes river, that is P, and Q is fishes die. Okay. Now from this statement is true, but can we say that the second statement that I wrote, if fish die, did chemical plant pollute river? Is this a true statement? Well, not necessarily, because if fish are dying, there could be some disease among the fish, some kind of viral disease. They could be dying because of that. Or it could be the case they could die because the chemical plant is polluting. Okay. So if fishes die, then Q could be then not necessary. So if fishes die, then Q could be either true or it could be false. So here is the thing that most of the time people make this mistake. When you say that P implies 2, they tend to think that Q also implies P. For example, if you have this statement, if chemical plant pollutes river, fish die. So that is a true statement, but you should not say that the opposite of that statement, if fishes die, chemical plant pollute river, that may or may not be true. Okay. So you have to be very careful. If Q are true, it does not mean that P is true. It could be true or false. Okay. But on the other hand, if Q is false, it does mean that P has to be false. So instead, what we have here is P implies Q and P. Both of these propositional forms are true. So it does mean that Q is also true. This is all it means. The chemical plant pollutes river. Okay, this is one thing that is true. And if that is true, then you know we can conclude that fishes die. So one question that you are asking is, can you use propositional formulas to describe the implication? The formulas that I already introduced, not, disjunction, and conjunction. So yes, so it has kind of a circular definition. If the statement P implies Q is a true fact, and the antecedent, which is P, is also a true proposition, then we can imply that Q is a true proposition. So this kind of thing we can prove. And it's a funny thing. It has you are defining implication using implication. Okay. Uh, okay. So there is a poll, implication in English. Okay. P implies Q. P, if P, then Q. Is this what it means? Yes or no? Q if P. Just reversing the order. Okay. P only if Q. Okay. So I have changed, reverse the order of P and no, I haven't changed the order of P and Q. But instead of saying if P then Q, I'm saying that P only if Q. And this suggests that P can only be true if Q is true. Okay. And P is sufficient for Q. If you prove P, then you can prove Q. This means that proving P allows you to conclude that Q is true. So, for example, if you show that n is greater than 4, then it immediately implies that n is greater than 3. It's an implication, because if a number has to be greater than 4, it must be greater than 3. So Q is necessary for P. For P to be true, it is necessary that Q is true. Or if Q is false, then we know that P is false. Okay. If Q, the thing that comes after the implication is not true, then we know that the condition at the beginning is also not true. Because if the condition is true, then Q should have been true. Okay. So we can say make statements like this. It is necessary that n is greater than 3. If we want, n has to be greater than 4. Okay. So these are kind of the different kind of statements we mean in English, and how they kind of translate into the logical form. Okay. Now let's look at the truth table for P and Q. If you want to understand this implication logically, let's try to see the truth table and whether we could express P implies Q in terms of the connectors, the logical operators that are introduced, which are and, or, and negation, because that will make it easy to understand, and you'll see. So let's try to create the truth table for the implication. So let's say P and Q are both true. So it says that and we want to see whether the statement if P then Q is true or not. Now, if P is true, so since P is true, I know that this statement will be true if Q also holds. Okay. And in this case, you can see Q is also true. So this implication is going to be true. Okay. Now let's look at the second case. P is true, but the condition holds, but the actual action, the conclusion is false. But the statement says that if the condition holds, then Q must be true. But it says that Q is false. So this is so it implies that this implication statement is going to be false. Okay? Other thing that we have is when P is false, the condition doesn't hold. Okay, then what can you say about this implication? So since the condition doesn't hold, it doesn't matter whether Q is true or false, right? Because the condition, if it doesn't hold, then I can say anything about the world. Okay, so suppose if my condition is sun rises from the west, if sun rises from the west, I can say 2 plus 3 is equal to 4. That statement is perfectly correct because sun never rises from the west, right? But this logical implication is still correct. Okay. So, but if you have false, the condition is false, then it doesn't matter what the Q is. Okay. It can be true or false. The logical implication is going to be true. So that's what happens. So we got a truth table for the implication, a propositional formula which is connected by the implication. The question is, can we find an equivalent logical propositional form which has a similar truth table? And for that, let me guess the propositional formula. Let me set it as not of P or Q. Now let's try to look at the truth table for not of P or Q. And this exercise you have already done before. And if you can plug in the values of P and Q in this formula, you'll first get true, false, true, and true. And this outcome of not P or Q matches exactly the column for P implies Q. Okay. And by the definition of equivalence using truth table, I can say then that not of P or Q is equivalent to P implies Q. Well, that's a very concise and easy to understand equivalence propositional formula for implication. Either P is not true or Q is true. Okay. And that's what it means to have the implication. And usually whenever I'm trying to reason about this kind of statements, I'm trying to prove theorems, okay, and other things, then I usually try to see them in this simplified form, which is the negation of the first proposition disjuncted with the second proposition, because I can easily reason about or and. The implication is kind of complicated. So these two propositional forms are logically equivalent. Okay. Now let me introduce a few other propositional forms which are equivalent to P implies Q or may not be equivalent to P implies Q. And the first one is the contrapositive. So P of Q, the contrapositive form of this propositional form is not of Q implies not of P, right? And so example, earlier we had this this statement, which is if the plant pollutes, fish die. Now the contrapositive statement would be if the fish don't die, the plant doesn't pollute, right? So I have swapped P and Q, their location, and I've also negated them. Okay. Contrapositive. If you stand in the rain, you get wet. So that was one of the statements we made. What is the contrapositive version? If I'm not getting wet, then I'm not standing in the rain. If you didn't stand in the rain, you didn't get wet. So, no, sorry. So this is not contrapositive. Okay. I'm just negating both Q and P. Okay. So this is the converse, not contrapositive. And if you did not get wet and you did not stand, then you did not stand in the rain. So what is this thing? It is not of Q and you did not of P. So this says that not of Q implies not of P. So this is the contrapositive version. The other one that I showed is not contrapositive. So logical, there is another notation I've been using so far, which is the equivalence, 3 horizontal lines. It means that the one on the left-hand side of this notation is equivalent to the propositional form on the right-hand side. That's what this notation means. P implies Q. If this is true, I know that this is equivalent to saying the fact that not of P or Q. This we already proved using the truth table, which is equivalent to saying not of Q is Q, right? So this is equivalent to saying that you basically permute. First, you get Q or not of P, which is equivalent to not of P or Q. And then you rewrite Q as not of Q. Okay. So now what you can do, you can now say this not of Q is a proposition and not of P is another proposition. Okay. And this form has similar to the implication form, not of something or not of something. So you can say that not of this something implies the not of this other thing. Okay. So by applying kind of this equivalence relations that we have derived so far, I can derive the fact that P implies Q is equivalent to not of Q implies not of P. Okay? And the converse of P and Q is Q implies P. And if P implies Q, this statement is true, it doesn't mean that the other statement Q implies P is going to be true or false. And we saw some example. And here is an example. If fish die, the plant pollutes. Okay. Can we say that? Well, if the fish die, there could be various other reasons. It could be because of some disease or something else. So this statement is not equivalent to saying if the plant pollutes, then fishes die. Okay. So these two statements are not logically equivalent. One does not imply the other. P implies Q does not mean that Q implies P, and vice versa. So this is something you have to keep in mind. And that is where most of the people make mistake. And if you do it formally, the way I described step by step, then you are less prone to mistake. And also if you do the proof, it can be checked by the computer to see whether you have made any mistake or not. So definition is, we have this definition, we introduce a new operator, which is this equivalence, logical equivalent. So we say that if we have two facts, one is P implies Q, P and Q are some arbitrary propositions, and the other fact is Q implies P, then we can say that P and Q are equivalent. They are logically equivalent. So this is just a definition. Now, okay. Now, I want to introduce another notion, which is the notion of variables. So far, we dealt only with propositions and the logical connectors. I introduced propositions, which are statements that could be true or false. And I introduced two concrete values, true and false, and also the logical operators, which are and, or, negation, and implication, and logical equivalence. Now, in addition to that, oftentimes you'll find statements where there are mention of things that are not fixed. For example, I have this statement which says, it's a mathematical statement, which says that if I sum the values, the numbers from 1 to n, then that is equivalent to n times n plus 1 by 2. Now, which one is a variable here? The variable is n. N is not given to you. Okay, n is not. It's kind of a variable, and its value could change. N could be 4, n could be 9, n could be 10. Okay, so this is unbounded variable. In the statement, you do not know the value of n, but no matter what the value of n is, this formula you are trying to assert, this formula is going to be true. Okay, so is I a variable? I is not a variable because I is bounded within this formula. You cannot change I from outside. Okay. The reason we use this I, it's for this shorthand notation. You can also explicitly write it as 1 plus 2 plus 3 plus dot 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 plus n. But this is a more concise way of writing it. The I is introduced to get this concise notation, and it cannot be changed from outside. So it's not a variable. It's not a free variable in the statement. Let's take some more examples. X greater than 2. Is X a variable? Yes, X is a variable and it's a propositional formula, but the value of this propositional formula depends on X. Okay, you haven't given the value of X. If you set X to be 4, then this formula is true. If X is say 1, then this formula is false. So x, the value of this statement that x is greater than 2 depends on the value of x. So, and x is a variable. Here is another statement, n is even and the sum of two primes, right? Here n is kind of the variable. You do not know the value of n. If we take n to be, say, 6, can we write it as a sum of two primes? 3 plus 3, yes. For n is equal to 6, it is true. For n is equal to, say, 8, no, there does not exist two, you cannot write it as the sum of two prime numbers, 8. Okay, so depending on the value of this variable, the propositional formula could be true and false. So now what I introduced is propositional formulas which have variables. So we call them predicates. And the predicates you can think of as Boolean functions whose value depends on the argument that you are passing. For example, if you pass in this predicate qx, which is x is even, if you say that x is 3, then this predicate is false. If x is equal to 4, you know that this predicate is true. So now your propositions are kind of parameterized with this kind of variables. And that kind of makes things interesting. And you have already seen as Boolean valued functions in 61A. Okay. So let me get back to this one. So this is a predicate, okay, and the value kind of depends on n, and in this case, no matter what the value of n is, it's always going to be true. The second case, again, it's a predicate. It depends on the value of x. So you can treat it as a function. G of n, the other predicate that I showed you, it's also a predicate because it depends on the value of n, the outcome, and it returns true or false. And if you remember Weston's experiment, then the thing that you are trying to say is person X flew. So that is also kind of a predicate. The person could be Alice, Bob, Charlie, or Donna. Okay. Person X went to Chicago. So that also can be used, described as a function. It takes the person's name and gives an answer depending on whether X went to Chicago or not. CX implies FX. So theory from Wesson, that is, this fact is true, and this is a theory, and you want to see whether this fact is true or false. And for that, you have to make some experiments. And it means that if person X goes to Chicago, then person X flew. In the previous cases, we made statements like if Alice goes to Chicago, then Alice flew. So that would be a concrete predicate without any variables, but this one has variables, and you can plug in the value of X and get different outcome. Next, statements about Boolean valued functions. So for that, I have to introduce the quantifiers, and I think I underestimated, overestimated the time that I need. So I may not be able to finish it today. I'll stop here. I'll try to cover it quickly, but the notes will be posted. And I think in the discussion section, if you have any questions in office hours, you can ask about the contents in the rest of the slide. So I will stop here.